Let's finish up section 5.1. So we've defined eigenvalues and eigenvectors, tried to motivate why one would be interested in eigenvalues and eigenvectors. We saw examples of how to compute characteristic polynomials, how to use those to find eigenvalues, and how to use the eigenvalues to find eigenvectors corresponding. We had some properties of eigenvalues. Now we're going to shift gears over and look at linear transformations. As I commented at the end of the last video, linear transformations from Rm to Rn are represented by matrices. Here's something new we can do with matrices, so here's something new we can do with linear transformations. This thing we're doing now is only good for square matrices, so that might have a little impact on the types of linear transformations that we consider. All right, so what we're going to do is define eigenvalues and eigenvectors for linear transformations. We're going to do it in such a way that it actually has a wide variety of applications, maybe beyond just the little matrix stuff, as we'll illustrate. So definition 5.2 is the definition of eigenvalues and eigenvectors for linear transformations, as opposed for matrices. Let T be a linear transformation of a vector space V into itself. So there's a restriction there. If we were using V equals Rn, we'd have a linear transformation from Rn to Rn, which would be represented by an n by n matrix. So we're back to the familiar setting that we had for the first part of this section. So linear transformation from a vector space to itself. A scalar lambda is called an eigenvalue of the linear transformation if there's a non-zero vector V such that T of V equals lambda V. Such a V is called an eigenvector of the transformation corresponding to eigenvalue lambda. Okay. If, as I commented, we had transformations from Rn to Rn, linear transformations from Rn to Rn are represented by matrices, the standard matrix representation, for example. So what we've got here then should coincide with what we had earlier when we were dealing with matrices. So if you're given a linear transformation, you want eigenvalues and eigenvectors, turn it into its standard matrix representation and find the eigenvalues and eigenvectors of those. It's the same thing. Here's an example in the setting of, it's an infinite dimensional vector space, D sub infinity, of all functions mapping R into R, which are differentiable of all orders. It's infinitely differentiable. This was mentioned somewhat back in section 3.2. So we've got functions defined on the reals that are infinitely differentiable. This includes, for example, all functions that have power series representation with infinite radius of convergence, to throw around some knowledge from calculus 2. Example 8 says, let D infinity be that vector space. Let T, map D infinity to D infinity, be the differentiation map. That is, the transformation takes a function to its derivative. Find all eigenvalues and all eigenvectors. All right, now this we can't address in terms of matrices. We'll do some examples in a second where we can. This we got to just go to the definition. So let's look at example 8. All right, and we'll follow our nose and see what happens. Okay, they want eigenvalues and eigenvectors. All right, so we're looking for scalars lambda and non-zero functions f, where the transformation applied to f is just some multiple of f. That is, the derivative of the function is a multiple of the function. Now, if we word it like that, you've had calculus 2, that ought to sound a little familiar. You think of any functions that when you differentiate them, you get a multiple of that function. Well, what if that multiple is 1? You know any functions that when you differentiate them, you get the function back? The exponential function behaves like that. We're going to see some other stuff, but we're going to see the exponential function in this. And it shouldn't be a surprise given the type of question that we're addressing. Differentiate and get a multiple of the function. We do have to break it into two cases where the eigenvalue is 0 and where it's non-zero. If lambda equals 0, eigenvalues can be 0, eigenvectors cannot be the 0 vector. If lambda equals 0, then we're applying the transformation to f, and lambda is 0, we're getting out 0 times f, we're getting out the 0 function. So we've got a function whose derivative is 0. Well, you know what kind of functions have derivatives 0 from calculus 1. They're constant functions. So we've got this satisfied when f is a constant function. Eigenvectors then are constant functions. We can't use the 0 function. That's the definition of eigenvector. Can't be the 0 vector. The 0 function would be the 0 vector in this particular vector space, d infinity. So when lambda equals 0, we get eigenvectors of the form. It's a vector space of functions, so the vectors are functions. The eigenvectors are f of x equals a constant, provided that constant is anything other than 0. Can't use the 0 vector as an eigenvector. A little more interesting is the second case. Suppose lambda is non-zero. Now, we still want the transformation applied to f to be lambda times f. The transformation is the process of differentiation. Differentiation is a linear operator. Might be words you heard in passing in calculus 1. Representing differentiation as a linear operator is valid, a linear transformation. So we get f prime equals lambda f. The transformation equals lambda times the function. Let's rewrite that. Maybe let y equals f of x and rewrite f prime as dy dx and y equals f of x. So the f prime becomes dy dx. The f function itself becomes y. So we've got dy dx equals lambda y. This might be stretching your calculus 2 knowledge a little bit. That corresponds to a separable differential equation. So we'll separate the differentials. So it looks like we're cross multiplying by dy. dy is not a quantity. Dy dx is not really a quotient, it's a derivative. Derivatives are limits of quotients. I could probably mutter the word chain rule somewhere in here and cover my logical bases. But it's common to solve these separable differential equations by rewriting that as dy over y equals lambda dx. We've taken the y to the other side and manipulated the dx somehow or other. It's maybe the meaning of differentials. Anyhow, we can integrate this. We'll integrate the left with respect to, let's see, it's a function of y. We'll integrate with respect to y, integrate the right with respect to x. So integrating 1 over y dy, integrating lambda dx will produce natural log of the absolute value of y. On the right-hand side, we'll get lambda x plus a constant. We're trying to solve for y, trying to get y as a function of x. We'll exponentiate. We get e, natural log, absolute value of y, equals e to this stuff here, lambda x plus c. C is some arbitrary constant or constant determined by initial conditions. It's usually how they're dealt with in terms of differential equations. Okay, the exponentials and the logs are inverse functions, so that produces absolute value of y. Right-hand side, we've got, using properties of exponentials, we've got e to the c, e to the lambda x. Exponential functions are never negative or 0. So the left-hand side's positive and so is the right-hand side. Y itself, I guess, could be negative. We've got an absolute value around it. So that produces y equals plus or minus e to the c, e to the lambda x. So this is the form of a function that behaves like that. And I told you I thought we'd see exponential functions. Maybe let k equal that stuff up front, either the e to the c positive or e to the c negative. we can rewrite this with that substitution then as y equals k e to the lambda x. So that's an eigenfunction. When I differentiate it, do I get lambda times the function? Yeah. You differentiate y equals k e to the lambda x. You get the derivative as k e to the lambda x times lambda. So its derivative is lambda times the original function, as was required right there. Chain rule sends that lambda out front. It does satisfy this condition here. Yeah, I thought so when we talked back up top about differentiating and getting a multiple of the function back. So here's the math behind why we get this, but that should make sense in hindsight, that we'd get exponential functions, something of this form. So we get y equals k e to the lambda x, where k can be any real number, or can't be zero. We did define it in terms of these exponentials over here. Oh, and it couldn't be zero, or we'd have the zero function, and that's the zero vector in this setting. So there's a moderately exotic example of this eigenvalue stuff in abstract vector spaces. Back to the notes. Okay, let's do some more examples. Let's just do the first two. The supplemental notes contain the others. The first two are mostly computational, if memory serves. Let's look at number 18. Okay, another linear transformation, a much more reasonable one, probably by our perspective. We got a transformation from R2 to R2. They say find the eigenvalues and corresponding eigenvectors of this linear transformation. Awesome. I'll just write it as a matrix. So we'll find the standard matrix representation, and then we'll do it like we always do in terms of finding eigenvalues and eigenvectors. That'll take long enough. Okay, so let's find the standard matrix representation. Remember, you apply the transformation to the standard basis vectors, the I and the j, two components in. So the standard basis vectors for R2, that's t of 1, 0 and t of 0, 1. You've got a formula up here so you can determine what those are. T of I is 1, -1. T of j is -1, 1. So we will put these vectors in a matrix as columns. 1, -1 goes in as a column. -1, 1 goes in as a second column. Unfortunately, in that matrix, this T of I also equals the first row. That's a coincidence because of the ones and the -1s everywhere. These go in as columns, as you'll recall when we found standard matrix representations. So there's the standard matrix representation of transformation T. Okay, you want eigenvalues and eigenvectors of the transformation? Well, that's the same as the eigenvalues and eigenvectors of the standard matrix representation. So we need to find the characteristic polynomial and its roots for the matrix A minus lambda I. Here's matrix A, subtract lambda I, that'll produce 1 minus lambdas along the diagonal. We'll need to take the determinant of that to get the characteristic polynomial. Do the multiplication, 1 minus lambda times 1 minus lambda, minus -1 times -1. This is the first time we've done one of these that didn't have a whole bunch of zeros in it, even though it's 2 by 2. That'll produce 1 minus lambda times 1 minus lambda, minus -1 times -1. You want to factor this. In the past, you were lucky, the handful of examples in the videos, they came to you factored. Here, we're going to have to multiply this stuff out and see if we can't rewrite it and then factor. So multiply 1 minus lambda times 1 minus lambda, FOIL it. Here we've got minus -1 times -1, that's -1. Rearrange it, that'd leave us with lambda squared minus 2 lambda, the 1 and -1 cancel. Oh, that's easy to factor. As will have to be the case. If it's too complicated to factor, we won't know how to factor. So that factors as lambda times lambda minus 2. So there's the characteristic polynomial. The instructions were find the eigenvalues and eigenvectors. Well, can't find the eigenvalues unless we find the characteristic polynomial, so this was necessary. Okay, set that characteristic polynomial equal to 0 to find the eigenvalues, and lambda equals 0 and lambda equals 2 are the eigenvalues. So we get lambda equals 0, lambda equals 2 for eigenvalues. We need to find corresponding eigenvectors. Okay, take lambda 1 equals 0, lambda 2 equals 2, right? Index them, express them in increasing order to be consistent with the way I'm doing it. That's not necessary, but to put us all on the same page. Now we need to solve two equations and two unknowns twice. Once for lambda 1 equals 0 and once for lambda 2 equals 2. Lambda 1 equals 0. We'll take the corresponding eigenvector, this vector v1 with the usual components. We'll consider a minus lambda I v equals 0 as a system of equations. Hey, lambda 0, subtract zeros along the diagonal. Of course, that doesn't change anything. We're actually finding the null space for matrix A in this one. Okay, so do your row operations stuff. We have a free variable coming. Yeah, you'd better. It's that story again. If you don't see a free variable coming, something's wrong. You don't really have an eigenvalue is my guess. But we'll do the row reduction, produce this, turn it back into a system of equations, rewrite it v1 equals, v2 equals, and so forth. Introduce a free variable. Okay, that produces v1 and v2 in terms of r as given here. So r can be anything except for 0. And we've got eigenvalues of lambda 1. So v1 must be of the form scalar multiple of the vector. Read the coefficients off. 1, 1. Oh yeah, you can't use a scalar 0 because v1 can't equal the 0 vector and be an eigenvector. Let's do it again. All right, so we'll have to do the same thing now with lambda equals 2. Lambda equals 2, system of equations, subtracting 2 along the diagonals. You can always pause the video so we can go through this without quite the same level of gory details. Put it in reduced row echelon form. We'll get something like this. Pivot-free column, better be when you're looking for eigenvectors. Rewrite as a system of equations, express as v1 equals, v2 equals, introduce a free variable, produces this, where s can be any real number except for 0 in terms of eigenvectors, which can be rewritten as negative 1, 1 is the coefficient, v2 is the form, any multiple of the vector negative 1, 1, well, except for s equals 0. So these are the eigenvalues and eigenvectors for the associated standard matrix representation. So they're the eigenvalues and the eigenvectors for the given linear transformation. This is a proof. It's a short proof. Let's go through the proof of this one. Prove that a square matrix is invertible if and only if no eigenvalue is 0. All right, already encountered some stuff like this. Suppose A is invertible. Then we know the determinant of A isn't 0. That was a result from chapter 4. You like computing determinants? No, I got better ways of figuring out if matrix A is invertible or not than taking determinants. But it's true that if the matrix is invertible, the determinant is non-zero. This might come in handy after all, because we've got all this eigenvalue stuff in terms of determinants. So there's where the theory's paying off finally. Well, if lambda equals 0 is an eigenvalue, then the determinant of A minus lambda I, that'd be the determinant of A minus 0I, that'd just be the determinant of A. We'd set that equal to 0. That equation would be satisfied if lambda is an eigenvalue. And we're getting a determinant of A equals 0. We just said if A is invertible, the determinant isn't 0. So the assumption that lambda equals 0 is an eigenvalue must be false. Otherwise, we get determinant of A equals 0, and we know the determinant of A ain't 0. So lambda equals 0 cannot be an eigenvalue. It leads to a contradiction. It says if and only if, so we've shown if the matrix is invertible, then 0 is not an eigenvalue. Let's do it the other way around. The other implication would be if 0 is an eigenvalue, then the matrix A is not invertible. It's actually the contrapositive of the other implication. Suppose lambda equals 0 is an eigenvalue, then we know the formula must be satisfied. We know that the determinant of A must be 0. Hey, if the determinant of A equals 0, that ain't an invertible matrix. That is, as theorem 4.3 was worded, this equation implies that A is singular. We said the determinant of A equals 0 if and only if matrix A is singular. Singular means not invertible. So there's a little proof involving determinants and involving eigenvalues and eigenvectors. And that finishes up this section. The supplemental notes have a few more examples in them, and I think the rest of them are a touch more theoretical than the one we did. But let's end this section there and on to section 5.2. I'll see you later.